radioactive particles, there are three that we're going to really focus on. We'll make ourselves a little chart. First is called an alpha particle. Then we've got a beta. And then we've got a gamma. An alpha particle is basically the same as a helium. So that's the atomic mass of helium, and that's the atomic number of helium. Remember, if we were to draw this, helium, I'll draw it off to the side. It would have 2 protons, 2 neutrons, and then 2 electrons. But all of the mass comes from that nucleus. It adds up to 4. Now the symbol for alpha that we use, we put 4 and 2 the same, and then we draw that little fish symbol for alpha. This is the largest radioactive particle. Now on to beta. Same as an electron. So we know that the mass of an electron is negligible. They are so teeny tiny, we don't include that in the mass number. So for mass, here we put 0. And then beta, we put -1. And the beta symbol is B with a tail. And lastly, we have gamma particles. No mass, no charge, just pure energy. And the symbol for this, 0, 0, and then gamma kind of looks like a Y. So we've got alpha, beta, gamma. Let's look at some examples of how these reactions occur. We call these decay because the nucleus is spitting out these particles, getting smaller. It is decaying away. So example 1. The problem would read, uranium isotope 239 undergoes alpha decay. And we're supposed to write the reaction. Well, this is where it's handy to have a periodic table. So it said uranium, I'm not looking at this mass, it told me the isotope is 239, so I don't care about that mass number. I do care about the atomic number though, 92. So the symbol for uranium is U, 239, element 92. It undergoes alpha decay, meaning it's going to spit off an alpha particle. And if I look up here, that's the symbol for alpha particle, 4, 2, alpha. Then it's kind of like solving a puzzle. You think to yourself, what plus 4 is 239? Well, that would be 235. And then you think, what plus 2 is 92? 90 plus 2 is 92. So now I look at my periodic table and see what is element 90, and that's thorium, TH. And so now I have solved this decay reaction and written out the equation. Let's look at example 2. Neptunium-240 undergoes beta decay. So I'm going to look up the atomic number for neptunium. It's 93. It's going to decay and spit off a beta particle, and the symbol for beta is this. I'm going to think, what plus 0 is 240? Well, 240 plus 0 is 240. What plus negative 1 is 93? And that negative always gets people, but it is 94. 94 plus negative 1 is 93. I look up element 94. It's plutonium, Pu. Lastly, example 3. Uranium-240 undergoes I've seen it written gamma decay or gamma emission. We've looked up uranium before, it's element 92. A gamma particle symbol is 0, 0, gamma. What plus 0 is 240? 240. What plus 0 is 92? 92. It's exactly the same, so those are always kind of like freebies if you get to a quiz, test, or assignment and you see gamma, because that 0, 0 does not change. It's just emitting pure energy. All right, that's it for notes for the day. Tomorrow's notes, we're going to cover this a little bit more and talk about some of the medical applications of radioactive particles in nuclear chemistry.